And we are live, and I think we are even, yeah, just spot on time. Hi there, Happy New Year. It's the first VKUG session, virtual Kotlin user group, sounds weird, Kotlin user group session in 2021. I do hear myself twice, so I should mute this one. Here we go. And with me today is Evgeny. Hi, how are you doing?
Hi, Holger, I'm doing fine. What about you?
Not too bad at all. I think I'm not as tired as you seems to be, but we're nearly there. We nearly made it through the day. You look well, and just to repeat this, I was very positively impressed by joining this Zoom call and already seeing everything set up. So looks like you are prepared. It's brilliant. To all the people joining, hopefully soon. We also have a JetBrains license for Ruffle. I will prepare something while you have your talk, Evgeny, and we'll post a link during the session, which will collect your name and your email address. I promise we won't use it for anything else other than this raffle, and I will announce the winner, I think tomorrow, and then delete the data. Let's put the Twitter handle in as well, so I can put you in there on Twitter as well. So best of luck, and I will shut up now and leave you in Evgeny's very capable hands. Enjoy it.
Thank you. So, welcome everybody. Today's session, as you might know, has a name Kotlin Java 4 till 16 code coverage and their best friend bytecode with a little subtitle, scandals, intrigues, investigations. So let's start. Before we start, my usual disclaimer. I work in such great company as SonarSource. You might know them. Producers of products such as SonarQube, SonarCloud. You might use our linters. However, today we are not going to talk at all about this product. Today I'm going to talk about the project on which I work in my spare time. So whatever I say has nothing to do with my opinion, with my employer, sir. They only can dream that they own my opinion, and that's it. So today we're going to talk about another product, which you also might know. It has a name at JaCoCo. Originally, this name is just an acronym of Java code coverage. So if you use it or don't use it, maybe write something in the chat so that we have some interesting statistics who came today for the session. While developing this tool, we test 11 and let's say half JDK versions, starting from JDK 5 up to nowadays JDK 17. That's why half, because we also test early access builds, which are not yet released. It's quite fun, actually. Sometimes we find bugs even in JDK. I would even say that mostly we find bugs in JDK, not in our tool. But of course, sometimes we do implement the new features in JaCoCo. And for example, here is how code coverage report for some Kotlin classes was looking several years ago in JaCoCo version 0.8.1. Without any changes in the tests or in this code, sometime later, code coverage report started to look like this. And why this happened, what are those features? This is exactly about what we are going to talk today. Before we really start, it's important to understand that JaCoCo gets all the information from the class files, not from the source code, not from the IDE, from the compiled class files, the files produced by the compiler. This is actually quite interesting fact. First of all, it simplifies integration into the build process. We don't need to rebuild your project. We just can launch the JVM with a Java agent, and all the information will be collected on the fly because class files are going to be processed not on the disk, but are going to be processed in the memory. Also, in this case, absence of source files actually is not a problem because they don't actually participate in the process of computation. Well, They are shown to you at the very end, only in the report, but for the actual measurement and even for the display, they are not required. In fact, the nice property is that you can generate code coverage report even without source files, just for some class files, and you would see how methods are covered, which classes were executed, which. This is also nice because Java language evolves, but the bytecode, which is written in the class files, evolves slower than the Java language. So this gives a hope that new syntactic sugar is easier for us to process and not supposed to require any dramatic changes in this tool as it works with the bytecode, which not so often changes. For example, we had no problem with support of text blocks just because it's a syntactic sugar over existing string literals. We almost had no problem with switch expressions because in the bytecode they compiled to the same thing as before. And of course, this opens the door to the JVM languages other than Java. So we don't need to process source code. We process the result of the compilation. Kotlin compiles into the class files. So we suppose it to work for Kotlin. Why suppose it? We're going to see today. What are the problems with this is exactly what we're going to see today. We're going to have a look into the class files. And here is a real disclaimer. Sorry, everybody, but today there will be blood of JVM, a little bit. Please, sorry, today we are going to have absolutely naked Kotlin compiler and Java compiler. We're not going to use IDE. We're going to use command line, execute compilation using the command line. Sorry, we're going to talk a strong language. As I already said, we're going to look into the class files. We're going to talk bytecode. And sorry for this, I will try within 1 hour do intense violence of your brain. Again, sorry. Please take a seat. Please feel comfortable. We together will try to go through all of this. Don't worry. And I hope you are ready. Are you ready, Holger? Are you eager to start?
I'm always eager. Go for it.
Okay, let's start with something what you know. So we are here in Kotlin user group. So I suppose we all came here to know something about Kotlin. Something deeper than what we already know, but we already supposed to know something. So let's start from Kotlin, not from Java. Let's start from something super simple, super easy. Let's start from an empty enum. So in Kotlin, we create enum, writing enum class bless me. Bless me is the name of enum. And inside of curly braces, I didn't write anything. So do you agree that this enum is empty? What do you think? I think it is empty. There is no constants in it, right? Feel free to drop your opinions in the chat.
The way you asked the question already bears bad news, but on first glimpse, it doesn't. But I do expect there is code happening behind it. So let's see what our... Okay, cool. We spoiled it.
Let's have a look what happens underneath. So what we're going to do today is pretty much the same operation. We're going to have some source code like this one, empty enum. We're going to compile it. We're going to do Kotlin C pass our source file. After compilation, we're going to use another tool. This tool comes with JDK. It's actually a standard tool, Java P, so-called Java disassembler. It shows us a readable form of the class files. It shows us bytecode. We're going to use two command line options of this tool, -v verbose and -p show me private protected, basically show me everything. This is two my favorite options of this tool because I can see everything inside. So we compiled our empty enum into class file bless me. We can see its content like this. So let's have a look. And as you correctly guessed, as we say in Russian, blessed place is never empty. So there is something inside. What's inside it? Probably this is already harder to guess, but there is some field. We had no constant, but this enum actually contains some field. Name of this field is $values. What is that? If there is some ideas, feel free to discuss in the chat, but I will just explain what's that.
Is it
just
is
in a second.
Are these placeholders or?
So if you also look at this field, there is something interesting in it. We could see in this disassembled output that this field is private static final. We could see it has flags. It is private static final. And it also has another flag, which is synthetic. Please remember this word, synthetic. We will get back to it just in a few slides. But let's move forward. What also we can see in this class file is that there is some static initializer. And this is where it gets interesting. In this static initializer, these field values get initialized. In this current case, this field gets initialized by an empty array. And the reason for this is that we didn't have any constants in our enum. If we would have a constant in our enum, then here we would see that every constant of enum is actually instance of this class, and it is placed in this array. So here is a constructor to construct instances of this class. No, it is private, nobody uses it because there is no constants. And here is interesting method that get generated. You might know this method in Java and in Kotlin. You could use the name of the enum, press a dot, and after completion will tell you there is a method values. Here it is. What this method values does is it simply returns you a clone of the field values. It returns you an array of all enumeration constants. So this field is just a cache. We don't need to always construct this array. We just can compute it once and later on return a copy. Another interesting method that gets generated, you also might know, it's a method value of. It returns you enum constant by its name. So here is an interesting thing out of this. Users do not write those methods in the source code, but they appear in the class files. So if you don't do anything about those methods, they would appear in code coverage reports because our tool is based on analysis of the class files. This was bothering our users, and it's fair. Why do you need to have some coverage for your methods values or value of? Why would you test them? Why wouldn't you just trust the compiler? Compiler does the right job. Not always, but let's hope. In most cases it does. So we need to exclude these methods. And this exactly was the feature introduced in JaCoCo version 0.80. We filtered the methods. Unfortunately, we forgot to filter constructor, and later on we realized that some people, okay, they do have empty enum where constructor is never executed. This bothers them. Don't ask me why people use empty enums. Apparently, for some people it's used. So we filtered also constructor. And here is how report started to look after all these modifications. That's what we're going to talk about today. We're going to talk about cases where the source code doesn't match the bytecode, where a compiler does something on your behalf, which is hard to predict. And it's interesting to look into what it does and why it does so. So as was promised, remember the word synthetic. Here we're coming back to it. This synthetic word, actually an attribute in the bytecode. We could find explanation about this attribute in the Java virtual machine specification in one of our Bibles. And the Java virtual machine specification says, if a class member does not appear in the source code, it must be marked using a synthetic attribute. The only exceptions to this requirement are compiler-generated methods which are not considered implementation artifacts. More precisely, default constructor, you know, there is also no empty classes. Each time you define a class without constructor, default constructor is going to be generated for you. And the two methods which we just saw, enum values and enum value of methods. They're generated, but they're not marked as synthetic. What else we could also find in the Bible is the synthetic attribute was introduced in backend JDK version 1.1 to support nested classes and the interfaces. Think about it for a while. And the question here would be, why for nested classes and the interfaces, it is necessary to generate some code and to introduce some attributes to mark the generated code. Can you imagine the example, or maybe you already know, of some source code, which after compilation would show us other examples of synthetic attribute, of something that was generated on behalf of you by a compiler? So I'll let you think for a little bit.
Yeah, give it some time to catch up on YouTube. I'm actually trying to get through my brain. So I'm not quite sure if we have something like when we define our main methods, there must be some generated magic as well. Jump in there, but let's see if we have Commander Zoe is so far leading in having the right answers, and us giving not quite enough time to answer. So, oh yeah, so let's see. We should be now at the point where everyone heard the question, and no one answers. So my bet is somewhere around the main class, but hit me.
That's not a problem. Yes, let's uncover this magic. So let's write a nested class. Let's write such an example. We have an outer class with a private field. This is Kotlin code. Then we have a nested inner class with some method. And this method performs access to the private field of an outer class, written in the same source file. The interesting question here would be, is it allowed? Does it compile? We're not gonna guess. Who knows. Actually, it compiles. Actually, this example was taken from Kotlin language documentation. It's just Control-C, Control-V of example of inner classes. It's also useful. We can just test it whether it compiles. So we could run Kotlin C minus JVM target 11 and our source file. Why JVM target 11? I'm gonna uncover a little bit later. So if you run this command, it's gonna successfully compile. This is a valid source code. If you're gonna have a look into the bytecode again, as we did for enum, Java P minus V minus P, and this time we have multiple classes. We have outer, we have inner. So let's first have a look at the inner, what happens inside of the inner class. We could see that it's indeed what's compiled for Java 11, as we ask it by JVM target parameter. That's fine. What we also could see, here is our method foo, which we wrote. But there is not any more access to the field bar as it was in the source code. There is actually a method invocation of a method in the outer class. And this method has pretty strange name, access $getBar $p. Why is that? Okay, why not directly access the field? Let's have a look into the outer class. In the outer class, we could see here is a private field bar. Here is this method which we spotted. It's public synthetic method. The reason why compiler has to generate this method is a misalignment between two specifications initially in Java 1.1. And later on, a misalignment of specification of Kotlin language and Java virtual machine specification. From Java language specification and from the Kotlin language specification, it's perfectly okay to access privates of outer classes. It's perfectly okay to access privates written in exactly the same source file. But from the Java virtual machine specification, there was no notion of nesting. Those two class files are two separate classes. They lie to each other next to each other, and strictly speaking, they do not have access to privates of each other. It would be a mistake to change the field from private to public, because then you could use this field, you could see it after completion, you could use it when compiling against this class file. So in order to solve this problem, this little hack was introduced. The hack is, let's generate the method through which we will be accessing private field, and let's mark this method synthetic so that it doesn't show up in the after completions, and so that actually compiler would not even allow you to compile code that tries to access synthetic fields or synthetic methods. Only compiler allow it to generate code which accesses those things. Why we compile it in JVM target version 11, you might ask? The answer to this is, here is our method, it returns field. So the answer why we compile it into Java 11 bytecode is because finally in Java 11, developers of Java virtual machine decided to fix this. And in order to do so, they introduced nest-based access control, nestmates, a special attributes in the bytecode, which let know to the JVM the relationship between classes, who is nested into whom, and who can gain access to the privates. Unfortunately, as we've just seen, Kotlin compiler does not yet take advantage of this and still generates those accessor methods. Hopefully one day this will be fixed in the Kotlin compiler. So let's move on. The logical outcome of what we've just seen is probably this. Java code coverage 2 or any bytecode processing tool should just ignore synthetic methods. They do not have any value for the user. They have only some value to overcome the JVM problem. And this is exactly how it was quite some time ago. From the beginning, we decided to ignore synthetic methods, and it was working. And it was working till the moment, and here where we switch a little bit on Java, where Java introduced Lambdas. And they take example of Lambdas, and we have to switch from Kotlin to Java because, as you might know, Kotlin, again, in case of Lambdas, doesn't take advantage of what was developed in the JVM. You might already know that there is some interesting thing in the bytecode behind Java Lambdas. So let's have a look at this interesting thing. We have such example. We have a class. It has one method exec, which takes a runable. It's a functional interface. We have another method fun, which just calls the exec method and passes into it Lambda as an argument. Pretty simple example, I hope. Please notice that there is a string literal joker in this Lambda. So now we're going to compile it. We're going to decompile it using JavaP. What we're going to see inside? We're going to see exec method. Nothing strange here. Indeed, we take runable and we invoke a method run on this runable. What is more interesting is probably content of method fun. And here it is. And indeed, there is interesting construction. There is instruction invoke dynamic, which is exactly the beast which was introduced in the JVM to support Lambdas. What's interesting here is that our string literal joker just disappeared. We had here system out println joker, and it's no more there. There is this magic instruction invoke dynamic. Where is our code? Where did it went? And here is compiler magic. And yes, another magic is, where is the line 9 where the joker was? There is no such line anymore. And here is magic happened. Compiler again decided to generate a synthetic method. This time it has interesting name. which starts from the word Lambda, $fun, $0. This is a mechanics behind invoke dynamic instruction. The content, the body of a Lambda gets compiled into a dedicated method in the class file, which is synthetic. So here is all the content. Here is Joker, here is system out, and here is line number 9. We're not gonna go deep into why it was implemented like this. It's just a matter of fact for us in this session. But you might probably go and already Google about invoke dynamic if you want to learn more about it. What is important for us is that, look, this method is synthetic. Our assumption that every synthetic method is not important for the user and should be ignored was actually wrong, because this method contains the logic that user wrote. Introduction of this method and invoke dynamic instruction actually broke our tool. Here is how code coverage report was looking in version 0.7.1. You might see that line 9 is not highlighted because we simply excluded. And we made a fix. We fixed this in 0.7.2. Maybe you might guess how we fixed it. If not a problem. I'm going to tell you. It's actually a fun story. We have to ignore every synthetic method unless method starts from the magic keyword Lambda $. We assume that methods starting from Lambda $, are generated by Java compiler for Lambdas only and for nothing else. This is a little bit hack on our side, just because there is a little bit of hack in the compiler. Hope this example was interesting. At this moment in time, you might ask me, okay, do I have something else than synthetics? Fortunately or unfortunately, I don't, but there is a lot in Kotlin. So let's get back to the Kotlin. Let's take some other example. And I hope now you are warmed up. Now I would speed up a little bit so that we don't run out of time. So no questions, please try to follow me. Here is example, data class. It has one field, x, of a type int. You probably already, as you warmed up, could guess what gets generated for this source file. Let's don't wait, let's just compile, let's just decompile, and I hope you guess it well. Here is a field, we wrote it, all good, but here is what we didn't wrote, getter method. It's got generated. What's interesting here, it's not synthetic. It's not at all any more synthetic, even though it was generated by the compiler. Here is another method, setter, also non-synthetic. Here is a constructor. Here is a method toString. It was generated, not synthetic. Hashcode was generated, not synthetic. And finally, equals. A big equals method. And nobody likes testing the generated equals method because there is a lot of branches. You might ask the question why these methods are not synthetic. If you remember what I said about synthetic methods is that Java compiler does not allow to write a source code which would call synthetic methods. So if developers of a Kotlin compiler would actually mark those generated methods as synthetics, they would break interoperability with Java. Then such a class file, such a data class would be impossible to use from Java, would be impossible to call a getter method. So instead of breaking interoperability, developers of Kotlin compiler decide to not do as written in Java virtual machine specification. They decide to not mark those methods as synthetic. Instead, they do another thing. For methods such as toString or hashcode or equals, they decide to not generate line number table. So the methods that do really correspond to some lines in the source code, there is a so-called line number table, which says this bytecode instruction corresponds to this source line. And for the methods that truly generated, which truly do not correspond to anything in the source code, like the generated method component 1 in this case, they do not have align numbers. This was a nice discovery. Actually, we got a help from JetBrains. They showed us this thing, and this allowed us to filter a lot of methods generated by the Kotlin compiler. So the report, instead of looking like this for equals non-tested to string non-tested, started to look like this. You don't need to test generated to strings and equals if it is a data class. You can just trust the compiler. So let's move on. A little bit more examples of non-synthetic constructions. You might know that Kotlin has unsafe cast operator. It is as keyword. You can cast something to something else. How it looks into the bytecode. If we're gonna compile it, again, decompile it using javac, look into our method where we wrote an unsafe cast, we are gonna see a null check. Compiler generates not only methods, sometimes it also generates a code inside of those methods. In this particular case, between instructions that we actually wrote in the source code and between instructions that were generated for our source code, we got something inserted by a compiler, a null check. Compiler has to guarantee that in this case, you're not trying to cast null to non-nullable type. And that's why compiler inserts a null check. Again, this is hard to test just because it's a safeguard. It's not supposed to happen. In our example, you could even notice that return string always returns non-nullable type. It cannot be null. There is no way to test this code. But there is a such safeguard generated by a compiler, so we have to filter it. So we write a special logic that processes the instruction, tries to find pattern of this null check and excludes it from the code coverage records. Funny fact, we wrote this filter and then we noticed that built-in code coverage tool built-in in IntelliJ IDEA, so developed by the same guys as developers of compiler by JetBrains, it actually has the exact same problem as we had. If you turn on a tracing mode, which shows you not only the line coverage, but also branch coverage, it's not enabled by default. It's quite slow, but you can turn it on. You would actually see that IntelliJ IDEA would be showing you a line as not fully covered, as having some branches on it. And those branches are exactly a null check. So we fixed it in JaCoCo. Maybe one day IntelliJ IDEA will also fix it. But okay, let's move on. Another interesting example is select classes. I hope you know that Kotlin has such a great feature. You can declare class as select, which means that you restrict which classes can inherit from it. You basically list them all. This allows you to do an interesting things like you can do, in Java terms, you can do switch by a type of a select class. And if you list all the alternatives, you don't need to write a default clause. This is pretty nice. Let's have a look on what happens inside of the bytecode. So we again compile it, we decompile it, we look into the bytecode. Here is our first case. You probably guessed it well. If it's instance of some class there in the bytecode, there should be instance of. Here it is, first case. Here is the second case, instance of a second class. And here is a third case. We didn't write the third case. As we said, Kotlin allows you to not write the default clause because we literally listed all the possibilities. Unfortunately, in the bytecode, you have to give to the JVM guarantee that at runtime, the third case cannot really happen. Because if you don't give this guarantee, what do you do here? You cannot fall through the methods. You cannot have some random code being executed. You have to do something in this case. If suddenly it happened that the third case appeared. So compiler on your behalf generates a default case, the third case, which simply throws an exception to indicate that something weird, something strange happened. We were not expecting any match, but we somehow got there. So again, we have to write logic, we have to write filter to filter this out. We did, all good. Same thing, same fun fact, in IntelliJ IDEA, you're gonna see these branches uncovered. That's fine, hopefully one day gonna be fixed as well. Let's move on. I hope you're not tired of examples on switches, and there is more. Let's have a look on quite interesting example switch or when expression in Kotlin. This time not for sealed classes, but for enums. We also know that for enums, there is the same trick. For enums, we can just list all the values of enumeration, and we don't need to list the default case. In this example, we don't need to list the third case. There is only two cases. If it's false, return 0. If it's true, return 1, right? Right. If you will look into the bytecode, I'm pretty sure that you already guessed it based on the previous example that Kotlin compiler will anyway generate a default case. So there must be something else if I'm giving to you this example, right? Let's have a look on what's else in there. So here is our switch. This time it's not if, this time it's not instance of, because in the bytecode, since the very beginning, we have actually instructions that corresponds to switches. This instruction is table switch. So here is indeed 3 cases. We already know answer on this question, why there is a third case, because, okay, here is first one, here is second, and again, in the third case, we say that it's impossible, we throw an exception. All good here. What did we miss it? Why I'm showing to you this example? What's interesting, we actually overlook it. It's just before the table switch. Before the table switch, instead of just doing a switch on the ordinal, which is integer constant corresponding to enumeration constant, we are doing something else. We are getting a field out of some weird class, and we load some value from an array. This field is actually array, and we load the value from this array. Why so? Let's have a look into this weird class. It's named funkt $when mappings. So we decompile it. We look into it, and indeed there is a field whose name enum switch mapping, and there is static initializer. And this static initializer does interesting thing. It does following assignment. The field is of a type array. So in the position of this array corresponding to ordinal value of our enumeration constant false, we put 1. In the position of this array corresponding to ordinal constant of enum constant true, we put 2. You might wonder why so. The answer may be not so obvious, so I will give it to you. The reason for this is that maybe we compile enum constant and the switch, maybe they actually in different projects. Maybe they actually one in the library and another one in another library. Maybe we compile them separately. And you know that if we reorder constants in enumeration, at runtime, the value returned by ordinal is gonna change. So if we would, in our original example, if we would flip false with true, then in current case, false has ordinal value 0, true has ordinal value 1. If we would flip them, the values would flip. And if it happened that our switch in some other library, which we do not recompile after such flip, by such a flip, we would actually break that library. So in order for this to not happen, we have to introduce this mapping. This mapping is basically mapping from the current runtime value of ordinal for particular constant into the value that was there at the compilation time, into the value that was used by switch. That's an interesting trick. Actually, the same trick for such a binary compatibility exists in Java. You could write exactly the same example, and you would also get some class like this generated. The only there only will be minor differences, like in naming of a field or in the way actually initialization happens, but the semantics are the same. Why this is interesting? This is interesting because if you will also recall that enumerations actually have static initializer, and this class also has a static initializer, if you combine those two things together, which we actually did at some other conference with Tagir, we had two talks. One talk was about switch expressions, another talk was about code coverage and bytecode. And we had those two pieces. He was showing a switch and I was showing enumerations. And then we had a talk and we come up with such an interesting example as enumeration with one constant, another enumeration with another constant. The first enumeration has initializer. In this initializer, we have switch. We have a method named neverCall. We have another switch in this method. And in our main code, we just print the constant of a first enumeration. So in this code, there is no single nullable type. There is no single null in this code. You might stare on it for hours. There is no nulls in it. But when you would execute it, it will throw you a null pointer exception. We're not going to go deep into this because we start to be short on time, and I still have some other interesting examples for you to show. Just believe me, if you want to try it at home, please try. It's a valid code, it compiles, and it's going to give you a null pointer exception. Please dig in home into the bytecode. You would understand why it throws a null pointer. Basically, it's a conflict of two static initializers. One static initializer generated for switches, another static initializer generated for enums. And they appear on the same execution path. And one of the static initializers wants value which is not yet computed. That's why you get a null pointer. So let's move on. Again, to filter this switch by enum, we had to write some code. All good, we did it. I hope you're still not tired of switches because there is more. Let's have a look at switch by string. Pretty simple case. We have a string and we want to match two values. One happened to be A, another happened to be B. And there is a default clause because we cannot enumerate all the possible strings. So this time we have to write the default clause. We have to write else. Such a simple example. Again, I'm not gonna spend time. If you know, you know. If you quickly guess it, what is gonna be in the bytecode, it's great. If not yet, please warm up because we are getting to more and more harder cases. So let's have a look what's inside. We compile, we decompile. Here's a switch, like a switch which we've seen in enumerations. But why there is two cases? We wrote a default and two string literals. There should be three cases, right? Why we see only two? Well, if you look just a little bit above, there is again trick. In order to implement switch by string both in Java compiler actually and in a Kotlin compiler for performance reasons, it's beneficial to first compute a hash code of string. Actually, it's already computed. It's actually already known. It's well specified. It doesn't change from the JVM version to the JVM version. So the hash code is stable. We can take a hash code of a string, and with a good probability, our strings would all have different hash codes. So there is nothing else to do. We already know which case it is. Unfortunately, I on purpose took an example where hash code of two string literals is the same. That's also why inside, after doing a table switch, we must make sure that we choose the proper case. So for the first case, we also have to call string equals, verify that we really got R. And here is the second case, which has the same hash code. We again should call string equals and we verify that it's B. If it is not, well, yes, okay, here is the default case. Interesting fact, in this case, Kotlin compiler is kind of smart. It generates just one table switch and okay, few branches with equals, quite compact bytecode. If you would construct the same case in Java, you would actually see that for some reason, Java compiler decides to use far less compact bytecode. It generates two table switches, some additional intermediate variables, etc., etc. So why it's important for us as the developers of tools that processes a bytecode, because we not only have to adapt to such tricks, but we also have to adapt to the shape of such tricks, because shape in different compilers different. So again, we write the filters both for Java compiler, for Kotlin compiler, and people no more wonder how it happens. I wrote 3 cases, but code coverage tools tells me that there is 8 branches. And now you know there is indeed 8 branches in the bytecode, because every comparison with equals requires you to have a branch. So let's move on. Again, same trick. If you look into IntelliJ coverage, we would see this uncovered branch. That's fine. Now I really hope that you warm it up, take a breath, and enjoy the hardcore. So probably you waited for this since the beginning. A most complex construction of a Kotlin language, to my taste, is actually coroutines, suspending functions, suspending lambdas. So here is a little example. We have 2 suspending functions. We have 2 suspending points inside. I hope we all know that this is a coroutines. I hope we all know that at suspension point, we might stop execution and actually give time to some other processing tasks. But how this is implemented in bytecode? Some time ago, I didn't know. So I did the same what we're going to do with you today. I just compiled it and decompiled it, and I was actually impressed of what's inside. Yeah, it should be pretty clear that such construction doesn't exist in Java, at least yet. So there is no bytecode instructions that would be helping Kotlin developers to implement it easily. They have to be smart, and I think they actually are. So they come up with pretty interesting bytecode with a big like this. I couldn't read it, you too probably, so let me zoom it a bit. It's still big. Okay, I will zoom it a little bit more. So here is our method. We wrote the method example. It had a signature which attempts a single integer. Now we got an example not only of compiler generating methods and generating some bytecode instructions inside of those methods, but we got an example where compiler decides to change a signature of a method. In this case, we have a second argument, a new parameter, continuation. So let's look at the body of this method. The body of this method starts pretty simple. We take this parameter and we check whether it is instance of some class. Again, this class was generated. It has interesting name, which includes our names that we wrote, but also some dollars. So this is generated class. Let's have a look into this class. Again, Java P minus V minus P, this class, what we could see inside. Indeed, this class is implementation of continuation, which probably realizes the interface that was used in the parameter. We could see here some fields. They have interesting names. They have name result, label, $0, L$0. So they probably hold some state, probably they hold some result. And it has an interesting method, invoke suspended. This method actually takes argument, and if you look into its bytecode, we would realize that actually this method simply calls the previous functions that we've just seen. So instances of this class, instances of continuation, can be used to invoke the method, and they are actually used to continue execution. And instances of this class indeed stores the state where execution was suspended. So let's go back to the previous big method. Let's see how the execution is suspended from the bytecode point of view and how it's resumed. So there is a little bit of initialization at the very beginning. We initialize all the fields of this continuation object. We initialize label, etc., etc. Yes, here's we initialize label. And then just after the initialization, there is again wonderful table switch, which I hope you now like. This table switch is done by a field inside of generated class, which is a label. Number of cases in this switch is 2 more than number of suspension points. 2 more, 1 just before the first suspension point, then after suspension point, then after next suspension point, and so on. So we had a constant, special constant string literal before the first suspension point. So we could actually see this suspension point. It's just before the invocation of method yield. Here we could see the code just after suspension point. We had a string literal after there. What is in between? We could see that after suspension point, we go to the continuation and restore the state. We take some fields out of it. We take the values of local variables, the values of parameters, etc., etc. And just before suspension points, logically, we save that state. Now, how the suspension point? Yes, here is save, restore parameters, fields, etc. Yes, okay. Save, restore of local x and save, restore of parameter. Now let's have a look at the suspension point. Suspension point is no more than just invocation of a method. And a check. If this method if this invocation indeed suspended execution, then we would immediately exit from the current method. If this invocation did not suspend execution, we would just continue after the suspension point. So you see, we go to the other method. If this other method suspended, we suspend also this one. Later on, we would be able to come back here just because we know at which point we stopped. We saved all the locals, and we have a little switch at the beginning, which could bring us back into the execution point just after suspension. Whew, that was tough, right? That was quite a lot. But I hope you're not tired, because I have finally example about finally. We're gonna have a look at this. It's also fun. You might breathe. It's far more easier than coroutines. So here is a simple example. Try finally construction. It exists in Kotlin, it exists in Java. Such a simple code. We have two methods. In one method, we do try finally. Inside of a try block, we execute another method. Inside of a finally block, we also execute the same method. I'm not sure already in which state your brain. I'm not sure whether you can think after seeing continuations or not. So I'm not going to ask you to guess what's inside of the bytecode. Let's just go straight and see what's in. We compile, we decompile, we look inside. What interesting could we notice here? We could notice 3 invocations of methods. Maybe I'm tired. Maybe it's only me who's seeing 3 invocations of a method, or maybe I did a mistake and on the previous slide really wrote 3 invocations of a method. So let's check. Let's count. So here is 1 invocation of method nope. Here is a 2nd invocation of a method nope. And is it third? No, it can't be third. It's a declaration of a method. So why the hell in the bytecode there was 3 invocations of a method? Probably I'm tired. To help investigate this, we need additional help. So let's use a marker. Let's add a parameter. As we did with coroutines, we will use magic string literals to help us understand what's in the bytecode. Inside of the method invocation in try block, we're going to put a marker try. Inside of a finally, we're going to put a marker finally. Let's compile, decompile. Let's have a look what's inside. So what's different? Now it's easy to spot. Here is try, here is finally, and finally again. Why so? Okay, I'm not gonna wait for possible ideas. Here is the answer. In the bytecode, there is no actually such a construction which represents a try finally. In the bytecode, there is so-called exception table. And exception table says, if exception happened from this bytecode instruction to that bytecode instruction, then please execute the exception handler. But we all know that so this helps to implement try catch. That's exactly try catch. If exception happened, it executes the catch. But this doesn't help much to implement the finally, because finally we know that finally should always be executed, no matter whether exception happened or not. So what compiler does? Well, compiler has to, in case of absence of exception, to duplicate the exception handler. And we get the duplicated bytecode here. Now you might understand why it's probably not a good idea to nest try into finally, because it's going to be duplicated exponentially, and sooner or later your class file will be enormously big. So a little bit of archaeology. Actually, what we've just seen was not always the case in Java virtual machine. If we will get back to Java, if we will look into Java 1.4, a long time ago, actually we wouldn't see the 3 invocation. We would see only 2. We would see exception handler and 2 magic instructions which are archaic nowadays. We would see instruction GSR, standing for Java subroutine, and instruction ret, return from subroutine. So a long time ago, it was possible inside of the functions write some other functions on the bytecode level. It was helping to implement try finally, but later on, it was deprecated and replaced by the duplication. If you're curious why this happened, you might look at the pretty interesting presentation of Nikita Lipsky about Java bytecode verification. All this actually relates to the verification of the bytecode. All this relates to this to the security. In order to be sure that bytecode doesn't do something strange, we have to verify it. And turns out that for verifier, it's pretty hard to process subroutines. It's way easier to process the bytecode when there is a duplication. Well, I don't know, Holger, if you allow me to go for a few more minutes, but I think
for it, definitely.
Running out of time. Okay, so finally, but this is not the end. I was coming to finally just to get back for a while to Java. We had a little bit of Java, but mostly we had a Kotlin. And you might get an impression that it's just in Kotlin we have a lot of such stuff generated on behalf of us, just because, well, Kotlin is a language that runs on the JVM, but which was not, basically the JVM was initially developed for Java. So probably the bytecode in the JVM is quite adapted for the Java, and that's why for Kotlin it's quite hard. That's why we need some additional tricks, etc., etc. Indeed, this was quite correct till some moment in time. Indeed, the bytecode in Java was evolving together with the Java language. But this changed not so long time ago. And even Java compiler nowadays generates crazy constructions, not as crazy as coroutines, but still crazy. And there is one more that I'd like to show you, which is try with resources. So I don't know when was the last time when you wrote a Java code, hopefully not so long time ago, but you might remember there is a try with resources introduced not so long time ago. So here is a resource, it's closable. Here is a new compact form of writing try block with resources which would be automatically closed. We don't need anymore to write cage, in a cage close the resource, and finally write another closing of resource, deal with all the exceptions, etc., etc. There is try with resources. And the rest compiler does for us. So let's have a look what compiler does for us. We again compile, we again decompile, and what we could see in the decompiled code is again a big beast. This time coming not from Kotlin, this time coming from JavaC. There is a lot of calls to the method close. There is 1, 2, 3, 4 calls of closable close. We already know why. Try with resources absolutely must close the resource. So let's do it 4 times to be sure that we close it. No, of course not. Of course, there is something else in between. There is some null checks, etc., etc. It will be quite hard to navigate just in this bytecode. So to understand meaning of this, I would actually resort to our other Bible, the Java language specification. Actually, when try with resources was introduced, the Java language specification was updated with a statement: the meaning of a basic try with resource statement is given by the following translation to a local variable declaration and an ordinary try catch finally statement, and bam, such a piece of code. So actually what is written in the Java language specification is that the try with resources that we've just seen compiles as like the following try catch finally would. There is absolutely no difference in the bytecode whether we compile the previous try with resources or such an example. In this moment in time, you could ask me, okay, man, I don't believe you. Like, they're completely different. One is a big beast, another one is just 3 lines of code. So please prove it. Okay, no problem. I can prove it. Let me increase a little bit of font. Let's go to the example. So what I have here is fun one. It's a try with resources that we've just seen. Here is a resource. Here is a try. We have fun too. This is a big beast, which also we've just seen. Here is a fun, a big one. Here is a resource again. What we're going to do, I'm going to compile fun1 Java P, fun1 Java. Out of this, we got example class. I'm going to decompile it and save result of decompilation into file 1.txt. I'm going to do the same with, let me remove example class actually, so that I don't trick you in any way. It's not there. Let me compile fun2 Java. It also produces example class. Let's decompile this one and save into 2txt. And now let's compare 1txt and 2txt. We're going to see a little bit of difference. We're going to see that modification dates are different, of course, because there was time difference between compilations. We're going to see that source file name was different. Indeed, I compiled them from 2 different source files. We're going to see that line numbers are different. Yes, just because line numbers are different. But nothing else. All the rest of the bytecode is exactly the same. Is there any bytecode? You might ask. Yes, if you open it, there is quite a lot of bytecode. There is constructor, there is fun method, and so on. So this source code produces exactly the same bytecode as drives the resources. So we can just look at this source code to understand what drives the resources actually doing. Let's have a look. Here's a try catch. We execute the body of original try. We catch an exception. If exception happened, we remember it in a local variable and we throw it again. Then there is a finally. Inside of this finally, we do a couple of checks. In case if exception happened, we anyway have to close the resource. In case of closing also failed, we have now 2 exceptions. We have to attach one to the other. So here we are. And that's where we use the save it exception. If there was no exception, we can just close the resource. And if exception happens while we're closing the resource, okay, it will be just thrown. There is no more 2, there is just 1. We don't need to attach. What is interesting is, you probably remember just a minute ago, we was talking about finally. We were talking that finally block gets duplicated everywhere on every execution path, whether exception happened or not. So you can imagine how many duplicates this code creates in the bytecode. And that's exactly why we've seen 4 times close. It's written here 2 times, but we've seen it 4 times because it's got duplicated. What's also interesting here is that Java compiler is was not extremely smart, because in this particular case, there is a guarantee that a resource is never null. The null check is not needed. So this can be removed in the bytecode. Another case is when we duplicate the finally into the catch, there is no need to anymore check whether exception happened or not. We already in the catch, we do know that exception happened. So there is another if, which is a dead code, becomes a dead code when duplicated. Bam. All this changed a little bit later. So if we take, so try with resources was introduced in Java 7. If we would take Java 8 compiler, we would see that there is less null checks, dead code elimination a little bit. If we go even further, if we take Java compiler 11, we still could compile to 8, but Java compiler 11 is smarter. There was 2 null checks, and now there is 0 null checks. It's a more compact code. So the compiler also evolves, it gets smarter. Why showing this all to you? For 2 reasons. One is we not only have to adapt to particular compiler, whether it is Kotlin compiler or Java, we also have to adapt to various versions of those compilers. because compilers also change the way they generate the bytecode. This is quite a tough job. And the second reason is also quite important. The task that we are trying to solve is actually unsolvable. What we are trying here to do, we are trying to understand, looking at the bytecode, whether initially it was something what user wrote or not. Whether user wrote try with resources or try catch. And unfortunately, it's unsolvable. As you've just seen, just looking on the bytecode, we couldn't distinguish a try with resources generated by the compiler from this beast of try catch finally written by the user. Hopefully, it's not a big problem for us. Hopefully, the cases where we cannot distinguish, they're always complex like that. And hopefully, users wouldn't write such beasts, they would just write try with resources. But if you would really do write such a beast, JaCoCo would tell you, well, I think it's try with resources, so you don't need to write tests for it, which is also not that bad, because you write try with resources exactly as compiler would. So we fixed the problem of try with resources. Users no more seeing missed branches, which, you know, as it is dead code, they are not just not necessarily in code coverage report, then totally unreachable. There is no way to test them. So we filtered them out. Now reports are better, as like for Kotlin. And here we finally come to the conclusion. The conclusion is, please be aware, the source code is not a bytecode. What you write in the source code is not at all what is gonna be executed by the JVM. Because JVM is gonna execute the bytecode, the output of a compiler. You have something in the middle between your source code and what JVM is gonna execute. This thing can trick you. This thing could trick you into the null pointer exceptions like we've seen in Kotlin, just because of the artifacts of this translation. Be careful. Not even bytecode is what's gonna be executed. You know, this is probably a subject for the other talk, but JVM is gonna take your bytecode, smash it all together, run a just-in-time compilation on it, transform it into the native code, and actually execute something which is result of compilation of the bytecode into the native code. Dragons also can be there. There might be bugs even in this translation. There might be other quirks. And even this is kind of not true because, you know, there is branch prediction. So processor is gonna also speculate about the native code, try to guess what you are giving to him and try to execute something else. And even this is not true because, you know, electrons in physics, they just pretend that they flow, but they don't. The second point is, as you've seen, bytecode-based tools have to do their best. They have to guess. They have to do the best what they can. So the tools like Java, JaCoCo, or tools like findbugs, handbugs, the tools that operate with the bytecode, they have a difficult task of mapping back the bytecode to the intention of a user. This is quite hard, as we've seen. So as this is hard, developers have to put up with this. We developers of a tools, or you developers of a tools, indeed have to put up with this and solve such a hard task at the best as you can. And you developers, as a consumers of these tools, please bear with us, with the developers of these tools, that it's quite hard. It's quite hard to know all the quirks of the compilers, to cover them and to filter them, and etc. etc. There is hard choices sometimes. So bear with us. And that's it. Now you can totally relax. And thank you for your attention. If we have time, any questions, even if we don't, maybe we can stay.
Oh, yes, we do have time. And we do have questions. Two of them actually at the moment. So let's see. Both from Margarita. So thanks, Margarita. The first one is, do you plan to implement such filters for Scala as well as you did for Kotlin? So you're not getting this question for the first time then?
Do you know a family name of this Margarita?
It's don't make me pronounce it. It starts with an N.
Okay, Netzelska.
Yes, thank you.
Okay, that's pretty funny. I think she's cheating.
Is she?
I think she is. Actually, she asked the same question. I was giving a talk oriented on Java, not on Kotlin, quite some time ago back in Odessa. And that was the same question. Yes. Do you plan to develop something for Scala like you did for Java or Kotlin? Well, yes. But, you know, the sky is the limit and the time is the limit. So if I get a free time, if I get finally some free time to get my hands dirty in the crazy bytecode of Scala, I would do something. We actually get some pull requests on Scala recently, which I also had to process. And yes, hopefully for Scala, the filtering also will be there and the code coverage reports will look better one day.
I see. So, Margarita, there is a good chance. And yeah, she just said that the previous answer was no. So she got a certain maybe from you now. So if she keeps on asking, no, and the other, it's a mixture of question and statement. Is, are there other interesting cases coming from latest Java versions? And she mentions sealed classes, records, etc.
Yes, actually, indeed, in records, there is interesting cases coming out. The recent addition to JVM, more and more users invoke dynamic instructions. So in records, you would find generated methods that use invoke dynamic. It's pretty much the same with records in Java as in Kotlin with data classes. Compiler on behalf of you generates methods like hashcode to string and so on.
Okay. And then we have a question from Alexander. And he asks, do you have a simple example for how it works in Java with Lombok? Does it work similar as in Kotlin?
For Lombok, something similar as for Kotlin. Okay, so even before, if my memory is correct, even before we started to work on Kotlin, we were getting a lot of requests about Lombok, and we did filtering for Lombok before we did actually filtering for Kotlin. But maybe we did not everything. So what we did for Lombok is pretty simple. There is a configuration option in Lombok. I don't remember its name, but it's Googleable. It's even in our wiki of our project on GitHub, probably findable. There is an option that enables generation of annotations lombok.generated for the methods that Lombok generates. So for example, if you use equivalent of a data class, but using the Lombok annotation and all the getters, setters, hashcode equals are going to be generated, there is a way to tell to Lombok, also please mark those methods with annotation generated. And JaCoCo, as of today, implements a filter that would just exclude everything if it's annotated with annotation whose name contains word generated. So this covers quite some cases of Lombok. It doesn't probably cover some other, like maybe snaky throws, because not the method gets generated by the body of this method gets changed. Unfortunately, we do not cover this. And to be totally transparent with you and honest, I don't think that we should. I personally don't like much Lambda, especially as today there is better alternatives like Kotlin, like latest Java versions with records, which finally, hopefully, solve all the pains that initially was solvable by Lambda.
Cool, cool. I did a quick search and I found an article. Okay, I will put the link into the show notes as well here. And the name of the configuration is add Lombok generated annotation. So essentially, it's well, adding some metadata to it. Perfect. So both Margarita, well, I just imply. So she said that last answer was no. So I take this as a thank you. And Alex just said, cool, thank you. I think he's happy. So let's see if we have any other questions. It doesn't look like it yet so far. All good. Also good to hear. Okay, yeah, fair enough. Cool. I think we had a pretty amazing evening. I love the example. So definitely thank you for that. And yeah, so if you could give me some links for later, so I will put them beneath the description here. And for all of you out there listening in and watching in, so thanks for joining. I will keep the raffle open for, say, another half an hour. So feel free to go in there. The link is in the chat. And then I will announce the winners tomorrow. Also, it's the coming negging, so please click the subscribe button somewhere down there. Click the like button, and if the person who clicked the dislike button could get in touch, I would love to hear why. It's absolutely fine. I'm just curious. Perfect. And on this jolly note, I wish you all a great evening and a even better upcoming weekend. And we see you hopefully